I'm going to go ahead and get started. Good afternoon, everyone. Thanks for joining us today. So we've organized an hour-long webinar today around some new projections on changes in heavy precipitation, as well as some examples of how that's been used already. And we have a little bit of time at the end for discussion, and I'll go into that in detail. I wanted to just start by welcoming you all. Highlighting that this most recent part of the work has been funded by 3 jurisdictions in the northwest corner of Oregon, City of Gresham, Clackamas County, and Portland Bureau of Environmental Services. But we're lucky enough to have some collaborators from previous work on the same lines joining us from King County, and I'll introduce them in a moment. But before I get started into all of that, I just want to go ahead and start with the Zoom logistics. I think after the last year or 16 months or so, everyone's pretty familiar. But just in case, here we are. Everybody's having a really good time here, by the way. Jeff was very entertaining yesterday in our practice call. And I just want to highlight, I think this should look like the screen you're seeing right now. And I just want to highlight a few things. If you want to make any changes to your audio settings, that's the lower left corner. You'll notice that you're not able to share a screen or unmute yourself right now or share your video. I can, in the question and answer period, I can unmute you if you raise your hand. I'll show you how to do that in a second. If you want to toggle your view, right now I'm showing it in a grid view, but there's other ways of doing it. That's the top right corner. Okay, so for asking questions, this is the important one. You can either raise your hand during the discussion period and I'll unmute you. Or you can use this Q&A function. It's just right next to the raise hand button there at the bottom. And either one is fine. There is a little bit confusingly still a chat. I'd like to ask you to use that for technical issues or commentary. I'll be tracking both, but it's better for us to track the Q&A. We can make sure to answer your question if it goes into that other box. All right, so that's the Zoom logistics. I also wanted to highlight, so the latest work has been funded by those 3 jurisdictions highlighted there on that first slide and at the bottom here. But this builds on a whole bunch of other work funded by a number of other organizations shown up here. The bulk of the funding has come from King County and the Amazon Catalyst program, and we were able to build on that with funding from these other groups and jurisdictions. Okay, so finally, I want to tell you who's speaking today. So we're going to start with the talk about the projections and the new tool that we built. That'll be by Harriet Morgan from the Climate Impacts Group at UW. And then we're going to have 2 examples of putting that data to practice from our colleagues at King County. The first is Jeff Burkey talking about using that in stormwater facility design modeling. And then the next will be Bob Swarner talking about their use both at King County of these new data in his case in wastewater facility design. So with that, I'm going to stop and hand it over to you, Harriet. Take it away.
Thanks, Guillaume. Share my screen here. Great. Okay, so like Guillaume said, my name is Harriet Morgan. I'm a researcher at the UW Climate Impacts Group. And today I'm going to be talking about how climate change is projected to influence heavy precipitation events. Specifically, we're going to be highlighting an online tool that we developed to help stormwater and wastewater engineers access and interact with these projected changes. So like Guillaume just mentioned, the work that we're highlighting today was funded by City of Portland, City of Gresham, and Clackamas County, and we're also leveraging funds from a handful of Western Washington jurisdictions who we worked with back in 2018 and 2019. So this picture, I think, does a great job of illustrating some of the impacts that heavy precipitation events can have on communities in the Northwest. So this photo is taken after an event that occurred on December 7th back in 2015, where just over 3.1 inches of rain fell in the city of Gresham over a 6-hour period. And this event was just slightly larger than their 100-year event. But as you can see, it caused a culvert to collapse in the road that was overlaying that culvert to split in 2. And this road was a major thoroughfare through the city of Gresham. It saw more than 35,000 cars per day and was a main access point for students who were attending an adjacent community college. So this obviously caused some serious disruptions for the community, but I bring this event up because I think it unearths a larger challenge for climate resilience in Northwest communities, which is that the design of many of our stormwater and wastewater systems are based on an underlying assumption that heavy precipitation events are static or unchanging, that the heavy precipitation events in the future are going to look like the ones that we've seen historically. And however, recent research has shown that these heavy rain events are projected to become more intense with climate change. And this is a pretty important statement because previous research on the topic suggested very little projected change in precipitation for the region. And what we've learned is that in order to get accurate projections of heavy precipitation events, we really need to be using regional climate models to simulate local scale changes in climate. So Cliff Maths, who's with the University of Washington Atmospheric Sciences Department, recently produced an ensemble of regional climate model projections for the Pacific Northwest region. So these new projections are the basis for the extreme statistic calculations that we've calculated and that we're talking through today. So we have 12 regional climate models at a 12-kilometer resolution, so that's a 12-kilometer by 12-kilometer grid cell. And what our results suggest is the potential for large increases in rainfall intensity. These results are going to differ depending on where you're looking in the Pacific Northwest, what metric you're looking at, what duration you're looking at. But overall, our results are generally showing larger projected changes in more extreme events. So, for example, the projected change in the intensity of the 25-year event is larger than what's projected for the 2-year event. And our results also suggest larger projected changes for shorter duration events. So the projected changes are generally largest for 1-hour precipitation duration and are smallest for the longest durations like the 48-hour or the 72-hour duration. So this slide is showing the projected changes in the intensity of the 1-hour duration for the 2080s. These are projections generated under a high greenhouse gas scenario, which is RCP 8.5. Projections are expressed as a percent change that's relative to historic conditions, which we defined between 1981 and 2010. And this table is looking at projected changes for the wharf grid cell that's closest to the Portland airport. So the leftmost column on this table, the total precip column you see over here, this is showing percent change in total precipitation for the water year. And this is included for comparison with the extreme statistics. And sort of the takeaway or the key message here is that the projected change in extreme statistics is much larger than the projected change in total water year precipitation. So columns 2 through 7 here are looking at the projected change in the extreme statistics for that 1-hour duration event across a suite of 6 different return intervals from the 2-year all the way up to the 100-year event. So if we decide to take a look at the 10-year event, so this is the 10-year 1-hour duration event, the results project a 32% increase in the intensity on average across the 12 regional climate models that we're looking at by the 2080s. So this ranges from a 1% decrease in intensity to an increase of 94%. So if we look across this whole data table, we can see some of those patterns that we highlighted on the previous slide being reinforced for this specific wharf grid cell. So specifically, those larger projected changes in more extreme events. So for example, the average change for the 50-year event is greater than what's being projected for the 5-year event. And this also brings up a caveat that I want to highlight, which is that the results for these higher return intervals should be interpreted with some degree of caution. And this is because the projected changes are calculated from 30-year samples, which makes it challenging to accurately estimate the statistics that are associated with these rarer events like the 50-year or the 100-year event. So the table that we just talked through is looking at projected changes for one grid cell, that grid cell that was closest to the Portland airport. So if we want to look at how these changes are going to vary across the region, we can look at these maps. which are showing average projected changes in the 2-year event. On the left side of the screen, we're looking at those for the 1-hour duration, and on the right side of the screen, we're looking at those for the 24-hour duration. Changes are shown again as percent changes relative to historic conditions, and these are for the 2080s under a high greenhouse gas scenario. So what do these maps illustrate? Again, we're seeing that point of larger projected changes for shorter durations. This is reinforcing that takeaway we pulled out on our first slide. So on the maps, we're seeing that the projected changes for the 1-hour event shown here on the left are greater than what's being projected for the 24-hour duration event on the right side of the screen. You'll also likely notice a fair amount of pixelation on these maps, and what that means is that there's considerable noise associated with estimating changes in these extreme statistics. So that's actually an area of future work that we're hoping to tackle, down the road, which would be thinking more critically about how we go about extracting robust trends from these extreme statistics regionally. And the final thing I'll close with on these maps is that we're looking at the ensemble average change, which is just the average of those 12 regional climate models. So we're not seeing any degree of model spread here or any uncertainty. We're just looking at the average. However, that model spread will become much more visually apparent when I switch over to the online tool, which I'm going to do now. So let me get out of my PowerPoint and bring up our visualization here. Great. Okay, so I'm going to do a quick walkthrough of the online tool that we developed in collaboration with the City of Portland, City of Gresham, and Clackamas County. So this gold lattice that you see here is the WRF model domain. Each of these grid cells, like I said earlier, is a 12 by 12 kilometer grid cell. And so here I'm zooming into the Portland International Airport grid cell again, or at least trying to. There we go. Okay. Getting very close. So this works in a similar fashion, though maybe not quite as fluidly as Google Maps. But once you select your grid cell, the screen changes, and now you're looking at the projected changes in extreme precipitation for that Portland Airport grid cell that we selected there. So we've intentionally designed this visualization as a pretty clean and simple interface to view projections for each WRF grid cell, and the tool provides 3 primary different ways for viewing the projections, and these are represented by these 3 buttons on the left side of the visualization here. So with this selection, you're determining what metric you want to view on the x-axis of this plot to the right. So you can view the projections by duration, which is the default here. So you can see we're including duration on the x-axis. We're including from the 1-hour duration out to the 72-hour duration. On our y-axis, just for clarity, we're looking at the projections expressed as percent change in the intensity of the event, and this is change relative to historic conditions. And since we're showing these projections as percent change, just to be clear, these results are based on the raw WRF projections. They're not bias corrected. So we can also view the projections by return interval. So if we select this button, you'll see here we're now looking at return interval, not duration on our x-axis. So we've changed that metric there. We go from the 2-year event out to the 100-year event. And then finally, we can also view the projections by decade. So we've for a specific duration return interval, we can look at these projected changes through time. These are moving 30-year windows that are centered on these decadal timestamps through the 21st century. And if you look at those red diamonds on the plot, which are the ensemble averages, you can see a clear trend in projected changes through the 21st century. So let's say we're interested in doing a walkthrough example focused on duration. So once we've picked duration, we have to select our 2 remaining metrics. So because we have duration, we need to pick our return interval. Let's say we're interested in the 5-year event. And let's say we're interested in looking out to the 2080s. So now that we've made those 3 selections, we're ready to sort of dive into the data a little bit more. So in terms of what we're looking at, this graph is showing the projected change in intensity for the 5-year return interval precipitation event for the 2080s. We have these different durations shown on our x-axis, And these projections are all generated under a high greenhouse gas scenario. So for each duration, you'll notice that there are 12 blue dots. So each of these blue dots represents projections from a regional climate model. And if you hover your cursor over one of these individual points, a tooltip will pop up, which gives you a little bit more information about what's going on behind that data point. What model are we looking at? What is the projected change for that model? Duration, return interval, time period, greenhouse gas scenario, etc. These red diamonds, like I mentioned earlier, are the model ensemble averages. So those are just the averages of those 12 regional climate models, and they also have an associated tooltip. So those are sort of all the main sort of graphical features that we've built in, but having this tool be co-produced with the end users, there was a real emphasis on building in some communication or shareability of this visualization. So we built in some download figure options where you just are downloading a PNG of the plot that you've created based on your selections. If you want to customize the plot, you can also download the chart data, where you get all the customized data selections that you made in a simple CSV like this. And then finally, we've also built in this download button, which enables you to download all of the data from this WRF grid cell without any filtering done. So you get all durations, all return intervals, all decades. So that's kind of the visualization in the nutshell. And as I mentioned earlier, since we're showing these projections as percent change, the results are based on the raw, not bias corrected WRF projections. So the raw WRF projections are really going to be most relevant to a design storm approach or technique. But we know that there are many applications that are going to require absolute precipitation totals, especially those that involve continuous simulation of stormwater. So in these cases, you know, it's really not going to be practical to apply percent change approaches to observed historical precipitation intensities. And so because of this, we went through and did a bias correction of the raw WRF to match observation rain gauge sites across Oregon and Washington. And these bias correction projections are going to be most relevant for use in continuous stormwater modeling or other detailed analyses. So here is a sort of a Google Map interface on a way to access the bias corrected projections. So these are all the different rain gauge station networks that we were included in the analysis. And so you would zoom in, let's say, for example, we're interested in the Hydra network. You click on one of these, you get a URL, you click on the URL and you're taken to this publication data infrastructure. If you click on BC WRF, and then here are all of the different data parsed in a variety of different ways. If you're interested in the time series, we have one of those for each of the regional climate models that can be downloaded there. I know this is a lot of information all at once, but we're going to provide the links, and we have a project page where all of this information is stored as well. So I'll close there, and now I want to introduce Jeff Burkey, who is a hydrologist with King County's Water and Lands and Resources Division. So Jeff is going to be sharing a bit about how the county has been using the bias-corrected projections and some continuous simulation work. So thanks, and take it away, Jeff.
Okay, I'm going to butt in really quick. Sorry, Jeff. We have 1 minute for any clarifying questions, and then I don't believe I remember to mention, but at the end of the webinar we'll have 5 to 10 minutes for a broader Q&A on all the talks. So I want to start by saying I put the link to our project website in the chat, and you can get the tool from there as well as get access to the data. And so then we had Harriet, we had one question from Curtis DeGasperi asking if we could say something about how realistic the 8.5 RCP 8.5 emission scenario might be.
Yeah, that's a great question. And I don't know, Guillaume, if you can speak to why. I'm assuming that Cliff's group was unable to do the projections for both RCP 4.5 and 8.5 just because of capacity constraints.
That's right.
Or funding constraints. So in an ideal world, we would have both of those greenhouse gas scenarios, because you can't make any sort of assessments about what's more likely than one or the other. But the reason that we're moving forward with RCP 8.5 is because that was the ensemble that we were had access to based on the WRF model runs.
Great. Thanks, Harriet. All right, so I see there's another question. We're going to hold off on that, and we're going to let Jeff go just to make sure we have time to get through all the talks. Thanks, Harriet.
Thanks, Guillaume. So I'll share my screen here. I'll do it right. Hi, everyone. Jeff Burkey, King County hydrologist, been doing watershed modeling for a number of years. And we took the data that Guillaume and his group and Harriet just presented and downscaled and bias corrected. So this project was funded by King County Department of Natural Resources and Parks. And also we had a pretty good grant from ecology as well that funded quite a bit of it. So we are data rich in King County. You saw all those points from what Harriet was showing. Here's just an example of the data that we have in King County for this project that we could select to use. And here I'm just showing the 12-kilometer grid. Each one of these greens is the centroid of the grid, if you will. And then the black triangles are King County rain gauges that we've identified as possible stations to use for bias correction. And I'm not showing, but there's 20 rain gauges in Seattle as well. So the really good dense network of rain gauges for many years. Some of them, a few of them, maybe a dozen or so, started back in the 80s. So long time series of rainfall. And similar to what Harriet just showed, for this project, we picked SeaTac because that's the kind of the typical regional rain area or rain gauge area that people kind of fixate on in this area. So we use SeaTac for our analyses in this project. And it's kind of fun to go through all the quotes that Einstein has, and one that I thought maybe a little bit apropos is, right, everyone's clever and we'd like to solve problems, but right, we want to try and avoid problems as best as we can. And like Harriet was saying, everything is relative. So we want all models are wrong, whatever adage you want to say, all models are wrong, some are less wrong. So doing everything relative, it basically kind of removes some of the noise of modeling error. So it may be wrong, but it's going to be consistently wrong. So that's why we want to do the relative aspect. And then also due to limited resources and time, we wanted to bookend things. So one scenario is using the RCP 8.5, and the other scenario is using the 4.5. Different GCMs though. So one is Access 1.0 and the other one is GFDL. So we try to do one wet scenario and one dry scenario, if you will, or less wet. It's probably more correct. So again, everything's relative. And like what one of the things I want to show is you're probably all familiar with IDFs, the intensity duration frequency curve. So here's just an example of SeaTac 8.5 2080s method used, and then each one of these curves. So this is duration. This is just a different way of showing what Harriet's tool is doing. Different duration storms and the intensity in inches per hour. And then each one of these curves is a return frequency, right? So the 1 year through the 100 year. And I wrote down that 3.16 inches, 6 hours. And if you equate that to 0.53, that's about a 10-year storm in the 2080s at SeaTac. So I thought that was interesting. And then the main thing here is this is kind of I like this to show the comparisons again to the 90s and the 2080s and the 2050s. The green is the 4.5 scenario, the solid line is the 2050s, the dotted line is the 2080s, and the orange line is the 8.5. So I'll just kind of pick out two things that are interesting. One, the obvious, right? The 2080s 8.5 says the 100 year is going to double for the the 1 and 2 hour. So imagine doubling the 100-year storm in the 2080s. That's a monstrous event. The other thing that's kind of interesting here is if you look at the 2050s for the 8.5, it's kind of similar to the 2080s, the 4.5. So that could have some benefits of we need to kind of do some surrogate analyses or something like that, that we might be able to do an analysis of one and say it's similar to another. So again, this is one location, 2 different models, 2 different scenarios, but I won't belabor that. But this is just a comparison to show the difference in the durations and all again relative to the 1990s there. So what did we look at? We looked at 6 types of ponds and seven actual facilities. Probably nothing really surprising here, detention ponds and infiltration and so forth. So these are the types of things that we evaluated when we wanted to do the analysis. And now what do we use to do the analysis? Maybe everyone's familiar, or most people are familiar with WWHM. It's the software that ecology basically promotes for doing stormwater facility sizing. It's developed by Clear Creek Solutions, Joe and Doug. And this is just a screenshot of things, but it's a continuous simulation. So it takes the continuous rainfall and you run it through a facility and you give it an objective of like forested conditions, maybe duration standards, and then it sizes it and optimizes it and does its kind of magic black box stuff and comes up with an optimal facility. So the steps though, if you're going to do that for WWHM, you need to add in your future rainfall. The other thing that kind of people don't really talk about is the potential evapotranspiration. That definitely needs to be corrected. The stuff that comes out of the WRF needs some adjustments. And then you need to set the time period because again, right, the rainfall is 100 years. The conventional standard right now is 30 years. Right? If you go longer, then you don't really have stationarity anymore. You probably have you don't even have stationarity in the 30-year window either. Everyone does it wrong. And then the other kind of thing that's kind of nuanced, but it's kind of an intriguing discussion is, we use forested conditions for the design standard, right? So that's nothing. That's not anything new. But when you're doing the 2080s, you're using the forested hydrology of the 2080s, not 1990s. So it's an intriguing thing because if you tried to size the ponds of the 2080s using the 2090s forested condition, wouldn't happen. It's just too much volume. We'd never be able to do it. So that's just kind of a little nuance there. And then the other part is to use what we did is I wanted to see how much model bias there is, right? Because I said everything's relative, but I wanted to see in an absolute way how far are the projections compared to what actual using CTEC observed rainfall is. And I'll talk at one slide to just kind of show that a little later. And so I mentioned the 6 BMPs. We picked one location, CTEC. We did 2 different land cover scenarios, commercial and residential, so kind of a high impact or high development and a low development residential. I said 6 types, but 7 BMPs, 2 soil types, right? Till and outwash or otherwise low permeability and high permeability for ambient conditions. And we looked at 5 different climate windows or time periods, whatever way you want to do it. So you think, okay, great, that's not that much, but right, all those kind of multiply up. And so you end up with doing one location, 140 BMP sizes. And so it adds up quick, so if you want to do another location, it'd be another 70, right? Because there's or something like that. So just kind of highlighting the number of BMPs that we evaluated given the time periods and soils and so forth. So it adds up pretty quick. And you kind of have to make sure you track all your files, that's for sure. And then just an example of some of the results. This is low permeability, ambient soils, relative again to the 1990s. On the left is 4.5, 2080s versus 1990s. And then these are the different things. So the commercial's a blue, residential's red, and then just the different BMPs across. And so basically, in the 4.5, you're seeing the increase in size relative to the 1990s using climate WRF to climate WRF. The increases are anywhere from 10 to 60% for till soils. In the 8.5, it's kind of similar, right? So it's, and we're trying to bookend things. So the 8.5, which is supposed to be the wetter scenario, it's also, 12 to 60%. So that was really interesting. If you look at the outwash soils, they're similar, a little bit bigger range. It goes up to 100%. And so that was not really bookending things as much as we wanted. The other thing I wanted to just show and touch on is the model bias, as I'm calling it, or model error, whatever you want to phrase it as. But on the left is the 4.5. So here I'm comparing the WRF 1990s to CTAC observed 1990s. And I'm doing it for the WRF from the 4.5 and the WRF from the 8.5. And essentially you can see that the 4.5, the WRF is generating bigger BMPs right out of the gate for the 1990s. So everything is bigger using 4.5 just from the get-go. So that shows there's a lot of model bias in the 4.5 in the plus. So the ponds are already going to be bigger before you even do anything. So that's good to know if you're going to look at absolute numbers. Now, the thing is, the 8.5 is the typical one, or more business as usual with emission scenarios, and we're closer on that kind of trajectory, right? So 8.5 is probably more realistic to where we're at as far as those atmospheric emissions. And the model does a pretty good job. So, the model bias for the 8.5 is, plus or minus 10%, and it's even closer than that for the other. So that's pretty good. And that means you can use, or you can certainly consider using the absolute terms in the 8.5 without having to worry about any introduced bias just from the get-go of the modeling technique. And again, all the data is bias corrected here as well using CTAC data. It's not just raw. And you can imagine all solutions are expensive, especially when you consider all the bump that's occurred over the last 100 years. Only in the King County area, at least 1990 and more recent, is when flow control really became at least a little bit better, and let alone water quality treatment actually didn't really kick in until 95, 98 or something like that. So a lot of stuff happened before flow control was even a big thing, other than trying to get the water down the pipe as fast as possible, which was before the 1990s. So what the county's been pursuing is we need to do things smartly because we don't have unlimited resources, and it's going to take and because it's going to be extremely expensive, we need to figure out how to do it smartly. And some of you may roll your eyes, but we're still in sustain. King County is still a sustain shop, and even more so with the current projects going on that wastewater is funding. So one of the tools that are available that we're also using is Sustain. It's a cost-effective optimization tool, and it basically can run thousands and tens of thousands of combinations of treatment trains of your BMPs, and you have an objective function, like you're trying to do flow reductions or duration curves or flashiness. So it'll go through the permutations, and you can get all these different scenarios, and you kind of start picking, well, if I spend 25 million in this, could be billion here, but 25 million, you can get to this percent. And if I spend 50 million, I can get to here. So you can kind of make some management decisions with this kind of tool. And again, this is this is in process right now for the county area, for most of the county area. So as part of the study, what did we really come up with as recommendations? Well, we were ideally hoping to come out with actual design standards or requirements, but right now, because we were trying to bookend, but the results weren't really bookending, we just kind of have some guidance at this point. Presumably in the next design manual update, we'll have some more information to support a stronger position on that. And with the projections, we also want to look at what's the capacity of the current infrastructure, culvert, road crossings, existing ponds. How much worse are they going to be? How much overtopping are they going to be? So we need to evaluate the whole infrastructure and then hopefully focus on where we need to address things first. Or if things need repair, we have the ability to say, okay, well, we need to size it more for climate change as well. And like I said, we did it at one location. And what was interesting is that the gridded maps of the outputs that Harriet was showing, you definitely can see the results when you look at other stations just in King County that you can get quite different results. And so just picking SeaTac would not be good enough. It would be prudent to do some other locations or do the regionalization like Guillaume was talking about. And we're hopefully pursuing the regionalization aspect in the near future. And we picked the 2080s. Well, so there's kind of some philosophy of, do you really want to design all the way to the 2080s and spend the money, or can you do some adaptive management? So should you pick the 2050s? And some facilities are meant to be lifetime, or others have shorter time spans, permeable pavement, like 15 years, or rain gardens. So there's all sorts of what kind of time periods you want to look at. You're going to have different things to consider. And then the kind of the more current thing is, because there's so much development going on, we're thinking about retrofit's clearly going to be the biggest thing, is because we need to retrofit everything everywhere practically. And how can we get the best bang for the buck for the stuff that's out there already? So we're also pursuing, like City of Redmond's also pursuing some dynamic controlled orifices, if you will, smart systems, if you will, that try and make the best effectiveness out of the ponds. And but the main thing is we only looked at 2 scenarios. We tried to bookend. Actually, the results were kind of intertwined and kind of similar. So now that we have the 12 or the 11 additional ensembles, the next step would to start evaluating those as well, and hopefully, if we don't increase the range, at least we understand where we fall in the whole gambit of results. And with that, I'll take questions.
Thank you, Jeff. We've got time for 1, possibly 2 clarifying questions, but I want to make sure we save time for our last talk from Bob. I don't see anything. The Q&A question that is there, I'm going to hold till the end. I think it's a great question, but that's not for Jeff. If you have a question, please raise your hand or put it in the Q&A, and I'll keep an eye on that.
Oh,
okay, we've got a question saving for you at the end, Jeff.
I put everyone to sleep.
On that note, let's move on to Bob's talk. Thanks, Jeff.
Hello, I'm Bob Swarner, and I'm the supervisor of the King County's Wastewater Treatment Division Modeling Group. And I will be presenting on assessing the impacts of climate change on the size of combined sewer overflow facilities in King County, Washington. I'd like to first acknowledge my co-authors that are listed on this slide, and they did the modeling for this effort. Today, I'd like to give you an overview of what we've done, and then why we did it, how we did it, regarding future climate predictions, rainfall adjustments, CSO modeling, and then finish up with the results of our analyses and the next steps. First of all, a little background about King County, our wastewater treatment division. We serve 1.9 million people. The colored shaded areas on the map are the 34 component agencies that we serve. We do the wholesale conveyance and treatment for these component agencies that have their local systems. The map with the red lines on the map show our conveyance facilities. We have 48 pumping stations, 25 regulator stations, and 3 regional secondary treatment plants and 4 stormwater plants, and 39 combined sewer outfalls. Now, this area here in the blue is Seattle, and it was largely constructed early in the last century with combined sewers, and that's where the stormwater is conveyed in the same pipes as the wastewater. And it works fine and gets the flow to the plant until it rains a significant amount, and then the wastewater system is overwhelmed, and their overflow locations around the city, 39 from the county system and 82 from the city of Seattle's system. So we need to control these to a limit of 1 per year. I'll get into that in a minute. But in order, that's what we're talking about today, is how we evaluate climate change impacts on how to control these overflows. So we obtained the output from 2 global climate models for 1978 to 2099. They were downscaled using a regional climate model with 2 greenhouse gas emission scenarios. And then we compared the 2070 to 2099 rainfall from the global climate models with the 1980 to 2009 rainfall in the regional climate model. And then we scaled the historical rain to produce the projected rainfall for the future. And we performed a hydraulic modeling of the baseline and 2 future climate scenarios, and then compared the required CSO volumes for the existing or historical rainfall and the 2 potential future rainfall conditions. So we have a consent decree with the Department of Justice, the EPA, and Washington Department of Ecology to have more than 1 CSO event per year over any 20-year window at each CSO location by the year 2030. And we know the climate projections for the Seattle area are for it to get wetter. And so if we size CSO facilities just based on historical, we are likely to be out of compliance, and we wanted to know by how much. Or in other words, how big do we need to build CSO facilities to accommodate climate change? Currently, we use calibrated hydrologic and hydraulic models to do a long-term simulation of 40 or 41 years of historical rainfall through the models, and then we calculate the size that we would need at each CSO location to have an average of 1 per year over the long term, and then 1 per year over any 20-year period. We bring those sizes to the project teams and management, and we describe our uncertainties in modeling and future projections, options for adaptive management, and then a decision is made on the size to build. But what we didn't have here, although the climate change was definitely an uncertainty, we didn't have that quantified as to how large these facilities might need to be if we sized them now for, say, the end of the century. So to get the climate at the end of this century, we'll call it 2080s, the UW Climate Impacts Group and a consultant team selected 2 global climate models and 2 greenhouse gas emissions trajectories. We selected the Axis 1.0 with a low carbon dioxide emissions peak, the 4.5, and then the GFD LCM3 global climate model with RCP of 8.5 for the high carbon dioxide emissions trajectory. And then the Climate Impacts Group downscaled the GCM output from these 2 models using a nested regional climate model with 36-kilometer and 12-kilometer grid. And then the consultant in UW Climate Impacts Group developed a methodology to factor the historical rainfall to arrive at 2085 conditions. And we're using these new rainfall files for sewer model simulations. So this graphic shows the extent of the models used. The outer box shows the extent of the global climate model results that were used, and then the nested 36-kilometer grid and 12-kilometer grid models. Those extents are shown in these inner 2 boxes. And we needed to get down to the 12-kilometer grid to really get the effects of the Olympic Mountains and the Cascade Mountains, which are on the west and east side of Seattle, respectively. The greenhouse gas emissions trajectories, the IPCC, these are the ones that were promulgated early, about a decade ago. Of the blue line is the 8.5 or the high carbon dioxide emissions trajectory we used, and the red line is the lower one, or 4.5, RCP 4.5, that we used. And over on the right shows the carbon dioxide concentrations that would result from each of these RCPs, ranging in 2100 from about 500 parts per million for the RCP 4.5 up to over 900 parts per million for the RCP 8.5. Now, temperature difference for the Seattle area, a couple of models were run for the 4.5 and the 8.5, and they were shown to, the 4.5 would have about a 6 degree Fahrenheit average to annual temperature increase from the last 50 years of the last century, to the 11 degree Fahrenheit difference for the 8.5. And the precipitation change, not as dramatic. It shows about a less than 10% average annual increase for both of those trajectories. Although there are many more models and there's a more higher range than that, certainly. So for the regional climate model, we have grid points or output at each of these squares, the red squares on the map, and we use these middle three, the northern one for the north part of Seattle, this middle part between Lake Washington and Puget Sound is Seattle. We have one near the center of Seattle in the middle, and then the south end of Seattle. So we use those three regional climate model output locations. And we compared the 1980 to 2009 data from the regional climate models with the 2070 to 2099 output. And then the way we did that is we took all the rainfall data on hourly output and we ranked those by intensity. And then we separated those into bins. The lowest 20% of the values we put in the first bin here, the next 20% in the second bin, next 30% in the third, next 20% in the third bin, and so forth. But as we got higher intensities, we ended up using more and more bins. So we ended up with 17 different bins. We took the values from the future climate at the 0.1 level of the future model and compared that with the 1980 to 2009 rainfall, and we came up with a factor of those. And then we did that the same with bin 2, 3, 4, all the way up to bin 17. And then we used that factor to factor the historical rainfall. The historical rainfall we split up into the same number of bins and factored that. So that's how we got the future rainfall. And what that comparison ended up with is the bottom 60% of the rain, we just used a factor of 1. So we did not factor it up. But as the rainfall got more and more intense, the future models are showing more intense rain. So we ended up factoring the upper 40% of the rainfall with factors of ranging from 4% to 20%. And then we use this northern grid point to factor this northern rainfall. That's so the yellow stars are the rain gauge locations. In fact, we use this northern grid point data to factor this northern gauge. And these 9 middle gauges, we use the middle grid point of the regional climate model to factor those, and then the southern 7 rain gauges we factored using the southern grid point. And the results of those were that the rainfall went from an average of 35.5 inches for the historical up to 37.9 using the low greenhouse gas emissions access 1.0 model, and that's a 6.9% annual increase. And the higher RCP 8.5 showed an 8.3% increase, up to 38.4 inches of annual rain. So we took that adjusted rainfall, and then we put those through our microurban computer models. We have in the green areas, the black lines show the delineation between the different models that we used. And we ran the 41 years of historical and future two climate scenarios, and we got CSO stats at these 16 locations marked by the red dots. And then we took that and the input that feeds this lower area. So we combined all these lower models into one model and ran that for the 41 years of historical and to future climate, and got the CSO statistics for these purple square, about 20 locations there. So the results. The top two rows are 18 locations right now we've simulated as in control. So in other words, they have one event or less per year in any 20-year consecutive period. But we found that half of those, or 9 of those, would become out of control in the future 2080s climate, and 9 would remain in control. So 9 would go out of control, 9 would remain in control. And we have 19 that were simulated as currently not in control, and we would require a control volume of 150 million gallons to keep those in control based on historical rainfall. And by the 2080s, we would need 216 to 237 million gallons. So that's an increase of 66 to 87 million gallons. That's the low and the high RCP scenarios. And that's an increase of 44 to 58%. So if we're going to size CSO facilities for the end of the century, we'd have to increase them 44 to 58% based on these two global climate models. And that's a hefty increase in cost as well. Our CSO program the costs are being calculated and yet to be published, but it's well over $2 to $3 billion just for the historical volume. So that's going to be a very sizable increase if we need to size facilities for the end of the century. Another important piece that we learned is that this is an example of one site where the 1-year recurrence interval volume is 5 million gallons. So that would be a control volume to control to the once per year criteria. The two global climate models results showed about 7.5%. So it's interesting that these two actually came out very close, even though there's quite a bit of difference in the greenhouse gases. But again, it went from 5 to 7.5. That's about 50% increase at this location. We also noticed that the 2-year event right now is about 7.5. So what happens as a 2-year event, as far as CSO goes, will become about the 1-year event at the end of the century. And that relationship has held for several of the locations. You can also note that the 5-year event becomes the 2-year event if you're interested in larger events. So possible next steps. So there are 11 other global climate model results that have been downscaled by the UW Climate Impacts Group. And we found that the 2 GCMs that we use do not actually bracket the impacts from climate change. We were thinking we were kind of picking a high and a low, but these were more toward the mean, and there are 3 to 5 higher and 3 or 4 lower. I'll show on my next slide how that looks, but We're going to use this information to help inform management on how to incorporate climate change projections into the sizing of CSO facilities. And we may do some intermediate years, for example, 2050, to see if the change over time is somewhat linear or more exponential. But this is an example of the scaling factors we would use for the 13 global climate models that were downscaled. And the dashed line is the mean of all of them. And as you recall, if you recall, our lowest 60%, we used just a factor of 1. This red line and the orange line are the two models we use. So when we get up to the higher intensity, we were pretty close to the mean of all these other models output. And there are several, 4 or 5 that are higher, and at least 3 or 4 that are lower in the higher intensity range. So we may do more modeling of that. So that concludes my presentation, and here's my contact information if you have questions. Thank you for listening.
We're waiting for Bob.
Okay.
Let's look at some of these questions in the Q&A. So that first question, so it's from, I don't know who it's from, it's anonymous, but asking if either Harriet or I could talk about some of the physical mechanisms responsible for the projected changes in extreme precipitation intensity in the region. So the short answer is that the research suggests that it's simply a consequence. It's the dominant effect is that warmer air holds more water. So it's a thermodynamic effect, as you would say it. So there's been a bunch of studies to see if we have more storms coming in, or if they're bigger or more powerful, and that research finds very small changes, if anything at all. So that's a minor effect. The main effect is just warmer air holds more water. Let's see if there's another question. Jeff, I think this is for you, from Shannon Reynolds. Are there any considerations to impacts for other systems, such as riverine or vegetation impacts, as a result of these forecasts?
Well, so we didn't look at that, but that's obviously, I mean, that's a possibility, right? Bank erosion might get become worse, right, with more flashness, with more magnitude of flows. So that's a pretty obvious one. And vegetation impacts, let's see. I don't really, in the hydrology aspect of things, the way I would say that may become relevant in our analyses is in the models we're using for hydrology, right? They're parameterized, so they kind of assume a certain level of soil permeability, soil storage, infiltration rates that have different vegetations on them. So they're going to respond a certain way, kind of because they're regional and calibrated. But when you start adding in more rainfall, they may kind of reach this trigger point where they change behavior. And is that real, or is that live, or is that Memorex? So is that real, or is that just kind of a result of how the model is configured? And that's something that we'd have to consider, because for the high infiltration soils, the vegetation definitely was responding a little bit differently. In the larger events, it basically was exceeding capacity. So outwash normally would generate very little in a forested area, but in the 2080s, it was generating a lot more because it was kind of changing from a high infiltration to a low infiltration because it was saturated and started generating more runoff. So I don't know if that's quite answering your question, but those are some of the things that would be considered, that should be considered when.
That was great, Jeff, and I think she was specifically asking about BMPs. I
Okay.
will add, Angela, that there is other work that we're doing, and actually hoping to host a webinar on later this summer on culverts that we're doing with Washington Department of Fish and Wildlife, which is tangentially related to changes in stream conditions.
And I would just add one more thing quick is, Ani at the Wazoo Extension is also looking at the effects of forest hydrology specifically And that's again late summer, if I remember correctly, or maybe early fall, when that study will come out. So keep an eye out for that.
Okay. Jeff, we're still waiting on Bob, who hopefully is able to join back in. There's another question for you, Jeff, from Angela Weiland. Hopefully I'm pronouncing that right. How did you assess forest conditions in 2080? So similar. And what was the basis for those future land use, land cover assumptions?
So when we were saying forest conditions as a target, we're assuming 100% forested. So like say for designing a BMP facility, say it's 10 acres of forest. And so we just say 10 acres of forest in the future as well. And like I was saying, we used the 2080s rainfall of the forested to compare to the 2080s rainfall of a development standard. And again, the 2080s forested is a different hydrology than the 1990s forested. So kind of, I don't want to say it's an esoteric or the academic kind of question is, or maybe it's not even academic, but you're kind of buying into the fact that the 2080s forest is good and not detrimental, even though it's completely different and more flashy than the 1990s. But you could argue, well, it's a slow transition. Maybe things adapt. Channels restabilize. There's all sorts of things you could kind of say. So the land use, we would just say like 10 acres or 5 acres. I think it was maybe 1 and 5 acres. We'd say residential would be X% of grass and X% of impervious surface. That'd get routed to the pond. And we try and match durations of the forested equivalent of those acres. And so that's how we take into account the future land use.
Great, thanks. Another question for you, Jeff. You keep turning off your video and I'm gonna call you back again. Joseph Pang is asking, I'm thinking about whether we are projecting the change of shape of hydrograph in addition to the change of intensity. I could answer that, but I think it's better coming from you given the stormwater perspective.
Sure. Using events for design, I think I think we should get away from that, and the county has. We're using a continuum of durations, and largely because antecedent conditions really drive things, right? However the soils are leading up to your storm event, your hydrograph, really drive, right? So you can have the same storm, but if you have dry conditions versus wet conditions, you're going to get a completely different response, and so that's why we have the ability to simulate continuously hourly, and it takes into account all the sequences and all the permutations of wet and dry and wet and super dry and so I would advocate going to a duration standard because that's how things respond.
Just to back up, I think that was a really good argument for the continuous modeling, and I would just add that I think there's an argument to be on, depending on where you're coming from, on any different number of strategies. Even not even a design storm approach, if you're not, depending on what you're doing, all strategies make sense at different levels of detail and in different places. So I think what we are providing in the projections is a change in the intensity for different durations, and that can get translated into a design storm approach in addition to the time series information we have from the model that is what Jeff used for his modeling. Okay, so Bob appears to still be experiencing technical difficulties, so we're just going to keep going with the discussion. It looks like we've got plenty of questions coming in, so feel free to raise your hand if you have any questions, and we'll just hope that Bob manages to get through his technical difficulties in the interim. So let's see, I do have one hand raised, and I want to see if I can find it. There we go. Okay, so this is Jordan. I'm going to unmute you, Jordan, so you can ask the question you said you had for Jeff. Let's see, did I do it? I think you're good.
Hi. Can you hear me?
Yes.
Okay, great. Thanks again for presenting So far, so good. I work for the city of Kirkland, and the biggest stuff I come across as one of the surface water engineers is developments that just sneak under their control requirements. And what I'm really hoping to see in the future is like some sort of a regional approach, because if we keep getting people that are 0.14 or even 0.154, which they try to round down, you add a few of those developments up, and sooner or later you have 1, 2, 3 CFS. And at this point, my neurons in my brain are firing off of like how I can possibly make these developments size their frontage improvements to have some sort of a premium on the size that they're saying, if they're either for varying by 10% and 60% in some of these events. Can I potentially up pipe sizes by 6 inches, assuming that it'll cover us for up into 2050? But is there any idea that a regional type of approach for developments or enforcements of the developments to consider their surrounding neighborhoods? Is there any ideas of that would come up maybe in a future manual, maybe even the manual after that?
Yeah, so you don't like the death by 1,000 cuts kind of?
No, I don't.
So yeah, I mean, clearly that's kind of a third rail, if you will, on a lot of aspects, because but the county definitely is talking about that. It's either reducing the amount of impervious surface that will trigger a mitigation or an LID standard. There's other ways to get at that. There's like trading of development rights, which is also a possibility, or in fee or lieu and fee and lieu things. But I get obviously I think everyone kind of experiences the same thing of people want to just get underneath the threshold of triggering stormwater mitigation, because it means they have to do more stuff. And the county is certainly still talking about lowering the threshold. And as far as region, right, that would be an ecology kind of thing. And I'm not directly in the stormwater design process like Mark Wilgus would be, but I'm sure a lot of that stuff that would be in discussion. It is in the county, but again, it's a very hot topic because it has a lot of implications. And King County, and I imagine for other jurisdictions, you would have to go through a very open public process, and there'd be a lot of review, and you'd have to, you'd get a lot of input, and hopefully people recognize what needs to be done. And so, I mean, I don't have the magic bullet or the magic answer for you on that, other than lowering the threshold that triggers is kind of the most straightforward and quantifiable, if you will.
Yeah, thank you. Yeah, the research shown today, it sounds like it'll take some time to turn the data into language that the everyday designer will be able to incorporate, but it's certainly a great first step.
All right, thanks, Jordan. Thanks, Jeff. Okay, so we had 2 other questions. I haven't heard yet from Bob, but it's looking like we might not, unfortunately, get to hear from him today. We did get a question from Matt Kurowski, who actually brings up one of the reasons we wanted Bob to speak. So Matt was asking why we showed data down to the hourly duration and not sub-hourly. In in a lot of urban contexts, you want to look down to even 5 minutes in some extreme instances, often 15 minutes on a routine basis for peaks. Our data is at an hourly time step. That's what the model is outputting to us. So we don't have sub-hourly information from the model, and that was partly intentional. As with everything, as you go to finer and finer scale, you're more prone to error, and so we chose hourly in order to improve the confidence in the results. The reason I brought up Bob's talk is that that's something that they dealt with in wastewater treatment division at King County, because they do, as it is highly urbanized, want to look at sub-hourly time steps. And so whereas Jeff showed a continuous modeling approach where they took our data essentially straight and pumped it into their model. Bob took a continuous modeling approach where they had historical data from observations that they scaled based on our modeling. And that allowed them to apply our scalings to the finer time step that they were using. Okay, and we have, this is great. Thanks for all the questions. And like I said, keep them coming. We've got time now. That's the one advantage. So the next question is from Dan Auerbach. Along those lines, would it make sense to bootstrap the realized runs to explore more of the interannual or intra-annual uncertainty space? And Dan, feel free to raise your hand if you want to clarify, but I think, you know, you're asking how can we better explore the uncertainty in the runs that Jeff was presenting on here. Dan's raised his hand, so I'll unmute him. Go ahead.
Hey, yeah, thanks. This is a critical question. I just was really appreciating everything that's been presented, but especially that acknowledgement of the sequence, you know, how much a sequence can matter. And so we could play with different sequences and get at a better spread. You know, you've got a lot of distribution in having the different and having the different ensemble members already, but within each of those ensemble members, you could re-scramble them and play with that. But you know, time and money.
Yeah, I totally agree, because I think the sequence of events, you know, when you look at the extreme statistics or even less extreme statistics, right, they're characterizing an aspect of things, but unless you're looking at, you know, including the sequence of events, you know, antecedent conditions, you know, I suspect you could see very different results. Especially on the smaller, especially if you're looking at facilities that are more sensitive to smaller storms, where the sequence may really matter more. I think the bootstrapping is an intriguing idea. That would be certainly a computational, you know, because when you're talking about doing the hydrology, running the model, I mean, it's certainly possible, and it would take a lot of scripting, I think, to make something happen like that. But I think that's a good idea. The other idea that we just talked about is what I call like the brute force of just running. We have the 13 ensembles, and presumably they're going to have different sequences just amongst themselves. And so we'd kind of cover that gambit just looking at, without even have to do a lot of work of the bootstrapping, we just look at the different ensembles. And I guess the bootstrapping, I mean, would you step it in, you know, 1 year, 5 year, 10 year? I mean, what would that kind of be, right? Because you'd yeah, I think it's a good idea. I think it's important.
Thanks, Jeff, and thanks, Dan. Bob, I see that you just were able to join.
Yes, I'm so sorry. I don't know why my Zoom isn't working.
Sorry for you.
Yeah,
no,
I apologize.
It happens. Well, why don't you stick around? We've actually been having a lively discussion, lots of good questions coming up. So there may be one or two that you can address if you don't mind sticking around for the next few minutes. And actually, this is great because actually, Tori, Ron, and Nishant, there's a question that's directed at you three. Trista Kobluski asks, for the jurisdictions that sponsor this work in Oregon, are they considering requiring a climate change assumption for sizing, conveyance, or facilities?
I can provide a quick comment on that. So should I go? Go ahead.
Please do.
I'll just say quickly, you know, we do a lot of our planning using asset management, and it's a risk based. And so this is climate risk. So we do plan on incorporating this into our work. The question is maybe what are those assumptions, or what are the processes? And you know, following up on some of the comments from Bob, we'll probably look at applying this in a number of different ways, not just like a design storm, but we're also looking at continuous simulation and kind of seeing how might those different futures look, and then figure out, okay, what's the most cost-effective way we can plan for that future accommodation. So that's kind of my simple. We're just in the processes of applying this data now.
And I don't know that I have anything else to add. I was just gonna say, I think we're still, we've got it. I think we're at this point, we're trying to figure out what it might mean for how we use this. But I think it was really valuable for us to have Jeff share and kind of figure out what they've been doing so far with this. And the fact that they're still kind of thinking about how to use this themselves, and with Oregon being slightly different than the way that Washington is set up. I mean, the thing about the Western Washington model is it is an ecology-led effort with the continuous simulation modeling. In Oregon, it really falls to each jurisdiction to figure out how they're going to approach things based on the permits that we have. So it's kind of a different approach, and a lot of us take, we kind of figure out individually how we are going to meet the permit conditions we've got. And at this point, adapting to climate change is something we're being required to do. I think it's something that we're all trying to explore right now. So I think there's going to probably be a lot of discussions over the next 5 years, kind of between the municipalities that have this information to figure out how we might integrate this. So still TBD.
Thanks, Tori. Do you want to add anything, Ron? You don't need to, but I want to give you a chance.
I'll be brief. Yeah, I mean, I think both Nishant and Tori, I think frame things pretty well for Oregon. We're in the process of adopting a new standard for flow control just now, moving to flow duration and continuous simulation. I really think our conversations have revolved around our next iteration of a model update for designing stormwater BMPs within our jurisdiction to meet our standards. That's likely where we'll have the policy discussion on how any sort of uncertainty for future precipitation events might factor into that modeling effort. And I wouldn't be surprised if that doesn't happen in Washington as well with the Western Washington hydrology model. So I think it'll kind of shake out then.
Great, thanks, Ron. All right, so we are at time. I don't want to hold anybody up longer than we promised, as much as I'm sure everyone wants to stick around past 5 on a Thursday. So I wanted to thank you all, Bob and everyone. I'm sorry for the technical difficulties. These things happen. We hope this is a conversation that keeps going. I hope to be able to organize occasional webinars like this in the future. So please keep an eye out for the future. And thanks again for joining us.